Good evening, students. Welcome to HashLearn. I'm your physics mentor, Sri Harsha. So we are in the chapter Wave Optics. So we have come to the second class of Wave Optics, which we have studied the few important, or I can say the heart of Wave Optics in the previous class, which is called as the wavefronts and the interference. The topic of today's class is diffraction, which is famously known as the special case of interference. Why do we call it a special case of interference? We'll see as the lecture goes on. So we have the diffraction is the today's concept, and as a regular drill we have the recap of the previous class. We dealt with the interference. So interference is, in simple language, it is called as the addition of waves. So the addition of waves using the concept of wavefront. So whenever you have the waves which are in same phase, the same phase waves, adds up to form a bright band, and if you have the out of phase, they will form a dark band. So same phase is bright band, out of phase is a dark band, and those bands alternate dark and bright bands form as we call it as fringes, or it is also called as interference pattern. Hi Preeti, very good evening, welcome to HashLearn. So the pattern will be something like this. So you will have alternate bright dark, so alternate bright and dark of equal width. And we dealt with the condition be bright dark, and it goes on. The necessary condition for whenever the path difference is equal to delta equals n lambda, this gives rise to a bright band, and whenever delta equals 2n plus 1 times lambda by 2, then it is giving rise to a dark band. And the distance between alternative bright and dark is called as a fringe width, which we studied using the Young's double slit experiment. Then the fringe width beta is given by lambda d by d, where lambda is the wavelength and capital D is distance between source and screen. And small d represents the slit width. So these are the things which we studied in the previous class. So it is just the important terms which we have discussed. So whenever you have same phase, they undergo bright band, out of phase they undergo dark bands. So that was the previous class discussion what we did. So now we have the today's class which we will go on. So that was the recap of the previous class, students. So now we have the most important CPP, which is the class practice questions. So we have two sources. The question says as it is, the two sources x and y emits waves of frequency of same value and same speed, but y lags x by the 2 pi l radian, that is the phase difference. If there is a maximum intensity in the direction of d, the distance xo using the integer n is given by, we know that the phase difference is 2 pi by lambda into the path difference, where path difference is delta x minus 2 pi l. So if you substitute that, you'll get it as ox is equal to lambda times n plus l. So that was the most important CPP question. Now we have the today's concept. So the goals of the today's class are like this. So we are going to deal with diffraction and the problems based on diffraction. So we are dealing with the concept called as diffraction today, which is also called as the special case of interference. The special case of interference, which is called as the diffraction. Now we'll go into the topic, this diffraction, into the details. So now let us start with the important concepts first. We will have the synopsis and then we'll go into that. So the first thing, before we start with the diffraction, there are certain terminologies which you have to remember or which we know, and one such term is called as shadow. What is a shadow and what do we see in the shadow is? So whenever you have an object, let us say you have an object, the object may be of any shape. Let us say it have a circular shape object, and then you have a light source over here which is incidenting the light on the object. And if this is the screen, you can see that in this region it will be a dark band, and outside this region will be a bright band. The shadow is the blocking of the light by the object. So that is the shadow, and we also call it as geometrical shadow. The reason why we take the geometrical shadow, why we call it as geometrical shadow is whatever is the geometrical shape of the object, the same thing is seen in the shadow. So what happens over here is when you observe a shadow, we see that, or if I take the ray optics into the account, imagine you have an object and you fire a bullet. So when you have an object, let us say the hand is my object and you fire a bullet. So surrounding this hand, I should see the bullet sticking, but this hand will block the bullets. So there will be a shadow formed. So this is what we have to expect if I use the concept of ray optics. But when I see in reality, it is something else. What is that something else? We will see in the course of this lecture. So geometrical shadow formation and is based on the concept of diffraction. So let us go into the one step ahead, that is the diffraction. So diffraction is a phenomena. It is a phenomena where the light bends, or you can say the phenomena of bending of lights. So phenomena of bending of lights are of the lights around the corners of the obstacles, and hence it enters the region of geometrical shadow. And this process is called as diffraction. So if you have a light and this is the obstacle, the light bends over the obstacles. The light bends over the obstacles and enter into the region which is called as the shadow region. So now what is the cause of this diffraction? What happens over here? We will see that. Now let us say this is a slit. So this is a slit and this is the screen. So this is my screen and this is my slit, or you can say this is the source of disturbance. So you have a parallel beam of light which is entering. So when a parallel beam of light is entering, it bends into the shadow region, and let us say there is a point P caused over here. Now for this, what we will do is I will assume a lens of focal length f such that it confines to a single place, and that point is point P. So now let us consider I'll have this place, I'll call this as A and B. Now let us say if the total slit width is D, this distance is D, and the path difference followed by the concept of the path difference which we discussed in YDSC. So let us say the path difference over here is, so if you assume this as your ratio, let us say the path difference between AP and BP. The path difference between AP and BP is equal to lambda. So is equal to lambda. So from this we will have the condition. So this is angle theta. So the D, or you can also call this as A. So the lambda will be equal to A sine theta is equal to lambda. So how is this A sine theta? If you take the sine theta ratio, you will have it as opposite by hypotenuse. Correct? So opposite is equal to, so a sine theta is equal to lambda. So, or sine theta is equal to lambda by a. So this is the condition which we are taking the first condition, that is a sine theta is equal to lambda, assuming there is a dark band formed over here. So now what we will do over here is, I'll consider a point C in between, and this is one more obstacle. This is the first thing about this, students. This is empirical, which doesn't have any proof. This happens like this, so we take the condition like that. So now what happens, the delta lambda, the path difference between AC and BC is equal to lambda by 2, which means AP minus CP is equal to CP minus BP, which is equal to lambda by 2. Now what happens when it is lambda by 2? So when it is having a lambda by 2 difference, which means, let us take the condition over here. This is the point P, and this is AP, and this is BP, assuming there is a lens over here, and this is CP. So A, C and B. Now the path difference between these two will be equal to, if there is a crest over here, there will be a trough over here. So what happens, these two will get cancelled out. So which means at the point P there will be a dark band formed. So there will be a dark band formed. So for the first, necessary for the first dark band condition is a sine theta is equal to lambda. For nth dark band, the condition is a sine theta is equal to n lambda. So if I take the condition of a sine theta is equal to 2 lambda, then the slit will be broken into 4 equal parts, 1, 2, 3 and 4. So here it will be lambda by 2, lambda by 2, lambda by 2, lambda by 2. So lambda by 2, lambda by 2, lambda by 2, lambda by 2. These two will get cancelled, these two will get cancelled. So there will be a dark band formed again. So now what is actually happening over here is, you have a wavelength lambda entering, you break that wave through a slit. So now what will happen, here it will be lambda by 2, here it will be lambda by 2. Lambda by 2 means what? If there is a crest, there is a trough over here, so they get cancelled out. So the necessary condition for minima is, in diffraction is, condition for minima in diffraction is a sine theta is equal to n lambda, where n is equal to 1, 2, 3. So this is the necessary condition for a sine theta is equal to n lambda, which was the condition for maxima. In interference. Hello Srishti, good evening, welcome to HashLearn. So this was the same condition. For maxima in interference. So this is the reason we call the diffraction as special case of interference. Now coming to condition for maxima. Now you have a slit, you have a lens placed over here, and this is the parallel rays which focus at a point, and assume there is a maxima or a bright band. Now I will assume the path difference is equal to 3 times lambda by 2. I am assuming, this is an empirical formula, it happens and there is no specific proof. So now what I'll do, I'll break this into 3 parts. So then the path difference, if I call this as A, B, C, D, and this is point P. So AP minus CP equals lambda by 2. CP minus DP is equal to lambda by 2. DP minus BP is equal to lambda by 2. So this is the first wave it reaches, second wave it reaches, crest, trough. So they get cancelled out, and this wave will reach the point P. So there will be a minimum amount of brightness. The second condition is, if I take it as a sine theta is equal to 5 lambda by 2, I have to break it into how many parts? Break it into 5 parts. So lambda by 2, lambda by 2, lambda by 2, lambda by 2, and then lambda by 2. This gets cancelled. The only lambda by 2 will reach the point P. So compared to this, this will have lesser brightness. So here in diffraction, the brightness is not constant like in the interference. In interference, all the bright bands have the same intensity, all the dark bands have same intensity. Whereas in diffraction, the brightness of the bright bands keeps on decreasing, the darkness of the dark band keeps on increasing. So the necessary condition for maxima is a sine theta is equal to 2n plus 1 lambda by 2, where n is equal to 1, 2, 3, and so on. So whatever, if you compare now the interference and diffraction, so you have two things over here. Maxima, the condition is a sine theta is equal to n lambda, and here the condition is a sine theta is equal to 2n plus 1 lambda by 2. Minima, the condition is a sine theta is equal to 2n plus 1 times lambda by 2. Here the condition is a sine theta is equal to n lambda. When you plot the curve of intensity versus displacement, the curve was like this. But here when you plot the curve of intensity versus the displacement, this is the central bright band and this is the first and the secondary maximas and minimas. So you can see that the intensity decreases with respect to distance. So this is the condition for the maxima and minima, students, which you have to remember. So this part is called as the central bright maxima. This is called as central bright maxima, which is formed due to the slit opening. So this is called as central bright maxima, and the intensity keeps on decreasing. So the brightness will keep on decreasing, the darkness will keep on increasing with respect to distance, and this was called as the central bright maxima. So this is the difference between the interference and diffraction. So you can remember it in an easy way. Whatever is the condition for maxima in interference, that will be the condition for minima. Whatever is the condition for minima, that will be the condition for maxima. So this was the diffraction for you. So now we'll go to the next step. So this is called as the width of the central bright maxima. The width of the central bright maxima, or we can also call it as central maxima. Now assume this is the screen and this is the slit, and this is the central bright maxima, which has a maximum intensity. So this is the central bright maxima and this is exactly at in between. Now if you take the ray which is reaching over here, so this angle is theta, and I'll call the width as W. I'll width as W. So that width is making an angle of 2 theta. The condition for maxima is a sine theta is equal to, a sine theta is equal to n lambda or just lambda. This is the minima over here. So first minima, condition for first minima is a sine theta is equal to n lambda, n is equal to 1, so a sine theta is equal to lambda. For smaller angles, sine theta is approximately to theta, so a is equal to, a into theta is equal to lambda, or theta equals lambda by a. Now let us assume this distance is equal to d. From the definition of angle, you will have it as 2 theta equals w by d. Correct? 2 theta equals w by d. So that is what we have taken over here. So now from this you will have it as, so 2 into lambda by a is equal to w by d, or w equals 2 lambda d by a. So this is the width of the central bright maxima. So this is the distance of the central bright maxima, the linear distance of the central bright maxima, and the angular distance can also be calculated over here. So we can also calculate the angular distance where theta is 2 to theta is equal to w by d. If you substitute, you'll get the answer as. So we know that 2 theta equals w by d. So from this you will have it as 2 theta equals, and the width is given by 2d lambda by a into capital D, which gets cancelled, 2 gets cancelled. So theta equals lambda by a, or 2 theta equals 2 lambda by a is the angle created at the slit. So this was the width of the central bright maxima, which is very important for the numerical problems. There is one small concept which is going to help us to solve certain problems, and that is very important according to me conceptually, and that is called as Fresnel distance. So that is called as Fresnel distance. So what is this Fresnel distance? So we know that whenever we have the light is having a property, and that property is called as rectilinear motion. So the rectilinear motion means the property of the light traveling along a straight line, and that is also having a limitation, and that is called as limitation of ray optics. And this distance is called as the limitation of validity of ray optics, which means it is valid till only that point. So beyond which the ray optics is not valid. So that Fresnel distance is the distance after which it starts deviating. The minimum distance after which the light starts deviating, that distance is called as Fresnel distance, represented by ZF. So we know that a sine theta is equal to lambda for the first condition of diffraction, it takes a deviation, or from this theta is equal to lambda by a for very small angles. So let us assume you have a slit and you have the screen. So instead of traveling like this, the ray has traveled a distance of x. This is the angle of deviation, and this distance is Fresnel distance. So theta equals x by zf. On substituting theta, you will have it as zf is equal to a square by lambda. So x is equal to a. If you assume, then you will have it as zf equals a square by lambda, and this is called as the Fresnel distance. So I hope you have understood this, students. If x is equal to a, then you will have it as z is equal to a square by lambda. So if that is the maximum or the minimum deviation possible, x is equal to a. So with this, we are good to solve the numericals. Now we have the first problem on your screen. A parallel beam of light of wavelength 500 nanometer falls on a narrow slit, and the resulting diffraction pattern is observed 1 meter away. It is observed that the first minimum is at a distance of 2.5 millimeter from the center of the screen. Find the width of the slit. So you have to find the slit width such that it produces a, diffraction pattern on a screen which is 1 meter away. Come on, students, solve it. So we have to find out, the first one is the theta, the linear distance in terms of theta. So the theta is equal to 2.5 into 10 power minus 3 divided by, that will be in the radians. So divided by distance. So we are taking this concept over here. So this is the slit and this is the screen. So this is 1 meter. So this is the slit width, which is equal to 2.5 into 10 power minus 3, the distance given. So theta is x by arc by radius. So 2.5 into 10 power minus 3 by 1 radian. So the condition for first minima is a sin theta is equal to lambda. For smaller angles, a into theta is equal to lambda, or theta equals lambda by a. So if you substitute the value, you will have it as lambda is how much? 500 into 10 power minus 9 divided by d is theta, or you have to find out the a, sorry. So a is equal to lambda by theta, where lambda is 500 into 10 power minus 9 divided by theta is 2.5 into 10 power minus 3 divided by 1. So which is equal to 500 divided by 2.5 into 10 power minus 6, which is approximately equal to 0.2 millimeters. When you solve this, you'll get the answer as, so this is twice, so this is, you can write it as 5 into 10 power minus 4 by 2.5, which is equal to twice, or 0.2 millimeters is the answer. So I hope you have understood this, students. So now we have the next problem on the screen. A screen is placed 50 centimeters from a single slit, which is illuminated with the light of 6000 angstroms. If the distance between the first and the third minima in the diffraction is 3 millimeter, what is the width of this slit? So again, you have to find out the width of the slit, provided the distance between the first minima and the third minima is given as 3 millimeters. So the first thing to be remembered, students, for all the numericals, so if this is the angle theta, this is the y distance, and this is the capital distance, so we will be using theta equals y by d. I won't be saying this every time. Hello Mahesh Babu, very good evening. Welcome on board. So theta is always fixed. For the minima condition, a into theta is equal to n lambda, because theta is smaller. So for the third condition, it will be equal to, or if you take for the conditions, that is y, and from this you will have it as a into y by d is equal to n lambda, or y equals n lambda d by dA. So for y3, it will be equal to 3 lambda d by a, and y1 is equal to lambda d by a. That is the minima conditions. So if you subtract this, you will have it as y3 minus y1 is equal to lambda d by a is constant. You will have it as 3 lambda, or 3 minus 1, which is equal to y3 minus y1 is 3 into 10 power minus 3, which is equal to lambda is 6000 into 10 power minus 10, and d is 50 into 10 power minus 2 into 2 divided by a. So from this, if you solve it, you will get it as a equals, again, a is equal to how much? 0.2 millimeters if you solve this. So students, I won't be repeating this again and again. This is understood. So this will also be taken into consideration, because sin theta for smaller angles is approximated to theta. So it is understood. For any question we can assume that, and theta is also equal to y by d is also constant for us. So I think it is clear to you, students. So now we have the third problem on the screen. In a single slit diffraction experiment, the first minimum of 660 nanometer coincides with the first maxima of wavelength lambda 2. Calculate the lambda 2. So first minimum coincides with the first maxima. So first n is equal to 1 for the minima will be equal to n is equal to 1 for the second wavelength lambda 2, such that the first minima coincides with the first maxima. Find out the lambda 2. Thank you, Mahesh. So for the first minima, the condition is d into theta 1 is equal to, so d into theta 1 is equal to n lambda, which is equal to lambda, or from this you will have it as theta 1 is equal to lambda by d, lambda 1 by d. So this is for the first minima. For first maxima, for first maxima you will have it as d into theta 2 is equal to 3 lambda by 2, or from this you will have it as theta 2 equals 3 lambda by 2 into d. According to the given problem, theta 1 is equal to theta 2, so we will have it as lambda 1 by d is equal to 3 lambda 2 divided by 2d, which gets cancelled. So from this you will have it as lambda 2 equals lambda 1 into 2 by 3, so which is equal to 660 into 2 divided by 3, which is equal to 220, or lambda 2 equals 440 nanometers. Srishti, I think you have made a small mistake in the calculation. It is 660 into 2 by 3, because denominator will go to the numerator, numerator will come to the denominator. So the answer is 440 nanometers. So I hope it is clear to you, Srishti. The next problem is on the screen. The light of wavelength 6328 Armstrong is incident normally on a slit having a width of 0.2 millimeter. The distance of the screen from the slit is 0.9 meter. What is the angular width of the central maxima? So now we know that the 2 theta is equal to 2 lambda by lambda d by d is what is the condition for the width. So you have to find out the 2 theta, so which is equal to, can I also write this as 2 theta equals 2 beta by capital D. So where beta is equal to lambda d by d, which was the interference which we studied. So which is equal to, when you substitute that, 2 theta is equal to 2 beta by d, or which is also equal to 2 lambda by d, or from this theta equals 6328 Armstrongs into 10 power minus 10 divided by 0.2 into 10 power minus 3. So theta is equal to lambda by a condition. So sorry students, we can start with the simple one. So theta equals lambda by a. So from this you will have it as lambda is 6328 into 10 power minus 10 divided by 0.2 into 10 power minus 3, which will be equal to 3164 into 10 power minus 6 radians. And we need to calculate the theta is this. So converting into degrees, you will have it as 3164 into 10 power minus 6 into 180 by pi. So 180 by pi. I'm sorry for the technical issue, students. So we will have it as so from this you will have it as theta equals, so theta equals lambda by a. So theta equals lambda by a. From this we get the value as 6328 into 10 power minus 10 divided by 0.2 into 10 power minus 3. So sorry, 10 power minus 3. So theta is equal to 3164 into 10 power minus 6 radians. So converting it, 3164 into 10 power minus 6 into 180 by pi. You will have it as 0.18 degree. but we need 2 theta, which is equal to 0.36. So the correct answer is D. Srishti, good. 4D is the correct answer. Thank you. Good job. Now we have the next problem on the screen. A slit of width A is illuminated by a monochromatic light of wavelength 700 nanometers at normal incidence. Calculate the value of first minima at an angle of diffraction of 30 degrees and first maxima at an angle of 30 degrees. So you'll have to find out the value of the A for the position of first minima at an angle of 30 degrees. So you have to find out the value of the slit width A. So this has to be found out, students. So for the first minima, we have the condition. For the first minima, A sine theta is equal to lambda when is equal to 1. So we will have it as A is equal to lambda by sine theta, which is equal to 700 into 10 power minus 9 divided by half. Because sine 30 is half, so which will be equal to 1.4 micrometer. The second condition is A sine theta is equal to 3 lambda by 2, or from this you will have it as A equals 3 lambda by 2 into sine theta, which is equal to 3 into 700 into 10 power minus 9 divided by 2 into half, which gets cancelled, so 2.1 micrometers. So the correct answer is 2.1 for the second one and 1.4 for the first one. So that was the previous problem, students, numerical problem 5. So now before we continue with the problems, we have the previous class contest question. The question was a wave of frequency 500 has a velocity. The distance between the two nearest point of 60 degrees out of phase is. And we have a new winner this time. Congratulations, Yogesh. You are the lucky winner of Atom session. So Yogesh, congratulations to you. So congrats, Yogesh. So with this, we have the next contest question on the screen. So you'll have to find out what is this. So time for the sixth problem, students. A real light of wavelength 6500 angstroms from the distance source falls on a slit of 0.5 millimeter wide. Calculate the distance between the two dark bands on each side of the central bright band. It is, the screen distance is given as 1.8 meters. Peru, why? So Peru has given option Y. What about others? I don't know. We will see the winner of the contest question to be announced in the next class. So students, if you have read the question properly, it is given central bright band. So if you calculate the width, that will give you the distance between, if this is the screen and this is the pattern, so this distance is being asked, which is equal to the width. and the width is given by 2 lambda d by d. So W equals 2 into 6500 into 10 power minus 10 into 1.8 divided by 0.5 into 10 power minus 3. The width will be equal to 4.68 millimeter. So instead of doing a sine theta is equal to n lambda on both the sides and then calculating the distance of x, the simple way of solving this is finding out the width of the central bright maxima. So now we have the next problem on the screen. Two wavelengths of sodium light 590 nanometers, 596 nanometers are used in turn to study the diffraction taking place at a single width of aperture 2 into 10 power minus 8 meters. The distance between the slit and the screen is 1.5. Calculate the separation between the position of the first maximum of the diffraction pattern obtained in the two cases. Wow, very nice problem. Separation between the first maximums. So please be thorough with the formula or the conditions for maxima and minima. Don't interchange it. If you interchange this, then your marks will also get interchanged. Instead of 1, you'll get 0. So let us say the x2 is the distance from the distance of the first maxima from the central bright band, which is given by 3 by 2 d lambda 2 by a. So this is equal to, so x1 will also be similar to 3 by 2 d by a into lambda 1. So x2 minus x1 is, you can take out 3d by 2d 2a as constant, and you'll have it as lambda 2 minus lambda 1. So 3 into 1.5 divided by 2 into 2 into 10 power minus 8. So 2 into 10 power minus 8 into 596 minus 590 into 10 power minus 9. So from this you will get as x2 minus x1 is equal to 6.75 millimeter. The separation between the first maxima is 6.75 millimeter in both the cases. So now we have come to the end of today's class, students. We have done with the diffraction and the numericals problems on that. So thank you for joining us, students. I hope you like this video. If you have liked them, please do share and help your friends. Now students, it's class practice pack times. It is available for passport members readily. For non-passport members, you have to subscribe to passport. And when you subscribe to passport, you only get CPPs. You will also get access to one-on-one doubt solving sessions and practice questions from the test, and the practice questions on the test from the best-selling books, and access to all the video classes covering the toughest concepts and problems, whatever you need. So with this, I'll take a leave. Happy weekend, but passport members, don't go anywhere. Solve the CPPs and then your weekend starts. Till then, keep smiling, keep solving physics. Good night, sayonara.